Hi, welcome to this lesson on calculus, sketching cubic functions. Let's have a look at some of the properties of a cubic function. So we said the cubic function has the form ax cubed plus bx squared plus cx plus d. So notice that this has four parameters, a, b, c, and d. So those are the four coefficients of our variables x. Okay, and then the d term is what we consider the constant term. Okay, because it has an x to the power 0 term there. So of these four, two of them, a and d, can actually tell us direct properties of the cubic function. So if a is greater than 0, then mostly in general, the function starts by increasing, reaches its maximum turning point, then decreases again, reaches a minimum turning point, and then increases again indefinitely. So it has this sort of shape. Increases up, turns, decreases, reaches a minimum, and then goes up all the way again. Why I say mostly in general is because if we consider just the normal function f of x equals x cubed, that is a polynomial function, a cubic function, right? A is 1, b, c, and d are 0, so it's still cubic. So the general form of x cubed looks something like this. It increases, reaches at 0, 0, and then just increases again. Okay, so it just continually increases. So that's why I say mostly in general will it have this shape here when you have more parameters involved in general. The same thing holds true when a is negative, less than 0. It does the opposite. It starts off by decreasing, reaches a minimum turning point, increases up again, reaches a maximum turning point, and then decreases again indefinitely. And again, I say that mostly in general because if you look at f of x equals negative x cubed, which is just a reflection of x cubed about the x-axis, it looks something like this. So it'll go something like this. Okay, so that's negative x cubed. And again, it just continually decreases. All right, so that's why I say mostly in general. So the parameter value of d, this tells us the y-intercept of the cubic function. And you can see why this is true, because if you plug it into the general form x equals 0, because that's how you find a y-intercept, all these terms vanish to 0 and you're just left with d. So the coordinate for the y-intercept is given by 0, d. So if d was positive, it would go up here. If it was negative, then it would go down here. So that is the y-intercept. That is what the value of d in this parameter tells us about the cubic function. Okay, so here is our checklist for the general methodology of sketching a cubic function. So we've been doing this inherently when we were doing all our previous questions that had some cubic functions in it. But here's the full precise methodology of what we're going to be doing when we sketch cubic functions. So first of all, you want to start by factorizing the cubic function. So if it's given in this form, the general form, then we want to get it into what we call the factorized form, which looks like that. A times x minus x1 times x minus x2 times x minus x3. So this x1, x2, and x3, those are the x-intercepts. How can I factorize that? That is where your factor and remainder theorems come into play. So that is why we had to study those. What about x and y-intercepts? Well, again, the y-intercept will be found from that d value if you have it here, or if you plug in f of 0 into the factorized form. And then x-intercepts come from the factorized form. That is why we need to know how to factorize a cubic expression. Then we want to find stationary points. That's when your first derivative is equal to 0. And then intervals of increasing and decreasing. And that's what we've been doing with the applications of the first derivative. Then the applications of the second derivative is essentially where we're looking for concavity. So we're looking for concave up or concave down, right? And any points of inflection. So inflection points. And again, your concave up has that shape where it lies above the tangent lines, and concave down has that shape where it lies down from your tangent lines. Once we have all that information, we want to plot all the intercepts, so your x and y intercepts. We want to plot the stationary points where the graph will most likely turn, and then we want to sketch the curve based on the properties of how it increases and decreases from the first derivative, and then what shape it bends in based on the concavity. So putting all this information together is the final culmination of being able to sketch a cubic function. Okay, now that we have the full methodology out of the way, let's go ahead and practice some cubic function sketching. Awesome. I'll see you in the next one.